Hello and welcome to How Long is a Piece of String live at MPL Open Day. We are delighted to be welcoming so many of you to the MPL site today to have a look around all of our labs and the incredible science that we do here up close. So just a few practical notes before we begin. If you're hard of hearing, it might help you to join our live stream on your mobile device because that'll give you access to auto-generated captions as our scientists are speaking. So you can do that by taking a look at the map and joining the live stream there. The exits to the auditorium are behind you, and here in the event of a fire, just leave calmly through those doors and then follow the instructions of our fire wardens. So, on to today and our 125th anniversary. So, MPL was founded in the year 1900 to standardize and verify instruments for testing materials and for the determination of physical constants. And since 1900, we have worked in every branch of physics and across all kinds of science and engineering in light, electricity, magnetism, radio communication, aeronautics, health, manufacturing, ship design, and much, much more. We have been at the forefront of some of the most amazing and impactful innovations in the world, from the development of the internet to improved cancer treatments, the invention of radar, and the development of atomic timekeeping, some of which you can have a look at just outside the auditorium here. And at the very beginning of MPL, 125 years ago, the then Prince of Wales gave a speech, and he said that MPL's purpose would be to bring scientific knowledge to bear practically upon our everyday industrial and commercial life, to break down the barrier between theory and practice, and to effect a union between science and commerce. And it's incredible to be here and part of an organization that's still delivering on that mission 125 years later. And hopefully, as you have a look around today, you'll see what some of that is about. So this is actually the second edition of How Long is a Piece of String Live. Our first was an event in March, which was all about the science of sports. But today the theme is all about myth-busting with metrology, and you'll be hearing about all kinds of things from orcas to phone measurement apps to oceans rising and much, much more. And first up, we have Allesio, who's going to talk about the science and fiction of science fiction, some of which you may recognize from our nice graphic here. So Allesio is a higher engineer working in our time department. Just outside of the auditorium, you can take a look at some of the amazing work on that yourselves. Do we have any Star Wars fans in the audience? Or how about, excellent. Star Trek? What about both? Oh, controversial. And possibly some Doctor Who and Battlestar Galactica as well. Well, if you've ever wondered how many of the things that we see in these sci-fi series and films could actually come true, Allesio is going to talk us through what parts have their grounding in some real science and what parts remain firmly fiction. So if you could welcome up to the stage, Allesio.
So, thank you very much. So, good afternoon, everyone. Hope you're enjoying the day so far. It just started, so there is a lot going on out there. Hopefully you enjoyed this talk as well. So yeah, I thought we could spend some time today talking about science and fiction in relation to TV series and films, and how much is true or how much is just fantasy. And of course, there are cases where you have stories which have a very strong fictional element, stories where they try their best to keep the scientific accuracy there, and things which are in between. And of course, in that case, filmmakers must be a very big effort in order to kind of combine the two things so that they can tell a very entertaining story while still have this scientific accuracy. So I love space. I work with, as an engineer, I work with space technology and lasers. So for me, one story which I really love is Star Wars. Star Wars is full of incredible technology. They got things like robots, actually droids, and lightsabers. And you might think that some of those things we are pretty close to get them. And in some cases that might be true. This might be the case of droids, or in this case, humanoid robots. This is the example from Boston Dynamics, who are making these very advanced robots that can do lots of incredible things. This is not even the latest model. Those things can actually walk, do cartwheels, they can do headstands and so on, though they don't have hands, in fact. So we are moving in that direction in that sense. But if we had to think about lightsabers, that's a little bit different. So light sabers are meant to be, in a way, swords or lasers. But if you had to use lasers, it would be difficult to have a real duel. It would be not so interesting. There would be no interaction between the laser beams. So not really a big thing. So a way to go around this could be to have to use instead plasma. So a plasma is a very hot ionized gas. You could use that to make the battle a little bit more fun. But that's not really achievable because you would need to bring with you some source of gas all the time, and then a high power source as well, which wouldn't be batteries, so you need to be plugged into the main all the time. So not really portable, not really fun, and hopefully we'll never need to develop anything like this, of course, unless just for fun. Still on the theme of space and Star Wars, another element of those films is explosions in space. Often you see those battles where large spaceships or small spaceships, they kind of get hit by something and they explode in place, very loud. And of course, that's not really something that might happen in reality. So one thing is sound. Sound needs something to propagate in space. There is no air, so there is nothing to propagate through, and so there would be no sound. An explosion like this would be really quiet. And also, in the films, those spaceships explode in kind of a localized way. They stay there. In reality, those explosions will actually lead to a very big cloud of debris flying everywhere, and all moving in the same trajectory as the initial body, like orbiting a planet, and so wouldn't be localized. And one final thing would be the way fire propagates. So I'm just waiting for the next image to appear. She's not. There you go. Flames behave differently in space, of course. One reason is the lack of gravity or the presence of microgravity, in another way. So that's a picture of an experiment from NASA where they compare the classical flame on the right on Earth, and then the more like spherical flame, which you would see in space. So quite a few differences. Still on the theme of space, of course, another example that comes to my mind is Star Trek. Star Trek is very different, of course, from Star Wars. It's a lot more about exploration, meeting more or less friendly alien species, and so going around on more or less large spaceships and exploring. One thing Star Trek did really well since it was first aired in the 60s, I think, was predicting the future. So in Star Trek, they show most of the things we now use nowadays on a daily basis. To give you a few examples, just trying. So they kind of show you things like communicators in the 60s already, which we now call smartphones. They have 3D printers. They call it replicators, and they manage to replicate things instantaneously, of course, it takes some time to do that nowadays, but probably we're getting there in a way. Then we got there you go. Tricorders in the series, which are basically health monitoring device. We now have health monitoring devices like smartwatches, which of course are not meant to be used for medical purpose, but we're also developing medical devices which are very small and compact, and MPL actually is helping with that. Other things they managed to portray early in the days were tablets. They call it pads, universal translators, and then they had these voice-activated devices. They had to say, computer, do this, computer, do that. Nowadays we give it a name. But it's basically the same thing. Now the next thing would be a little bit less about space, more about aerospace. When I was studying aerospace engineering several years ago, I remember I got very impressed by one film that was about a superhero flying in air with an armor made of some metals, and that, of course, is Iron Man. But if we had to be more accurate, precise, maybe Iron Man is not the right term, better be or Titanium Man or similar. Just because titanium is a much better choice of material for a suit like this, and they probably say that in the first film as well. That's, of course, it's unofficial. So when I first watched Iron Man, I remember seeing things that I was studying at the time, and I was really impressed by seeing that in the film. One thing was the fact that they had to go with the ice forming on lifting surface when high enough in the sky. So they had this issue in the film, and I remember studying that thing. And then several years later, I worked for a company doing aerospace engines. And I had to kind of investigate that almost on a daily basis. So that was in the film, and that's something that is actually reality. And of course, while progressing with the series and with the films, things moved a bit too much towards nanotechnology, so that element of realism got a bit lost. But that's okay, it's sci-fi or fantasy. Talking about stories where they try to balance realism with fantasy, a very good example, at least for me, would be Interstellar. There you go, too much. There you go. In Interstellar, one thing they do really well, in my opinion, is kind of showing how a black hole would look like. In the film, it's something like this, something like the picture on top, and that was actually just fantasy. It was the result of work from a big team of scientists and engineers working together with the filmmakers in order to come up with simulations based on real equations, and so the real theory behind black holes, and so eventually managed to portray this black hole in the film. And if you have to compare it with the first image, real photo of a black hole, it looks a little bit different. I see that, but just because what you see there is actually it's not the black hole itself; it's the material being ingested or digested by the black hole. So it's kind of emitting light. And that photo was actually a result of a massive work of collecting data from several telescopes around the world, merging this data and synchronizing that through atomic clocks, and then eventually obtaining something like this, almost like from a Earth-based telescope. So quite a lot of work. And then I would say there are cases where they try really hard to keep some element of scientific accuracy, and they fail a little bit, just because they want to they want to exaggerate things in a way that the public can actually enjoy the film a little bit more. And for me, that would be Gravity, the film. So in Gravity, lots of things happen. It's all due to gravity, of course, as the name suggests. They do a great job in kind of showing the effect of potential catastrophic events happening in space where things collide and debris are formed. The effect is exaggerated, but something like this can actually happen in reality. So almost every day, satellites in orbit around the Earth, they actually need to make some collision avoidance maneuvers. Because of debris flying their way or other satellites risking collision with. So that's something like, it's a real thing that happens every day in terms of and posing a danger to satellites and to astronauts who actually, sometimes they have to shield themselves, let's say on the ISS, in the most protected parts of the ISS, in order to avoid being hit by a little piece of debris. Even if it's a little piece of debris, the speed is such that it could cause a lot of damage. So one thing that gets exaggerated in the movie is actually something that it happens in real life. And then just to finish off, I wanted to give an example of something which is not really meant to be accurate, scientifically accurate, but it's just a work of fantasy. But I like that because at some point they talk about quantum, and they work with quantum stuff, and also makes me laugh. So that one is Ant-Man. In ant-man, they can shrink themselves a lot to the size of an ant, of course. They shrink everything, cars included. They say that they can conserve the mass of the things they shrink, then they ignore completely that, so that you can see the guy carrying around lots of Hot Wheels. It would be pretty heavy. So it's completely ignored at some point. But one thing they do at some point in the series, they shrink themselves even smaller to subatomic level, to a point where they can enter this quantum realm. So in the quantum realm, which in their case is a fantasy world, things are not, so the laws of physics are not really the way they would expect. In the films, there is like an entire universe hiding in this quantum realm, so it's really a fantasy world. But the quantum realm for us, working on quantum technology, is an actual thing. So if in the films this is like a place, when you're talking about quantum technologies, that's actually more like a description of a specific set of physical laws. So they both share this element where the quantum realm is a realm beyond our current understanding, where the laws of physics behave in a different way compared to what we expect. And so, yeah, it's kind of a true thing, but not a real location. So these quantum strange effects are different just because we are really tiny. So they are different from the macro world. And we can see those things in technology like optical clock or atomic clocks in general. Some of those we are developing at MPL. Of course, at MPL we don't do just quantum, we do a whole range of things. That's just a fraction of what we do. So I would say after these talks, go around, explore every lab you can find open, of course with permission, and talk to people that will be really willing to talk to you about what we are doing here. And enjoy the rest of your day.
Thanks so much, Allesio. One thing, so where you're saying in Star Trek that they had to say computer, but that we have smart speakers so different. I discovered recently that if you have an Amazon Echo, you actually can rename it to computer.
Nice.
You're not obliged to then do a Scotty computer, but you can if you really would like to do that.
Why
so
not?
Exactly,
if you
it's quite an enjoyable thing. Do we have any questions for Allesio from the audience at all? Anybody, a burning question about a sci-fi film or a series that you've loved that you'd love to ask a time scientist about? Yes?
Faster than light travel?
Faster than light travel, yes.
So
warp speed.
So while preparing this talk, actually, I found that someone at NASA came up with a concept for a warp drive where you can potentially go fast. Not sure you can go faster than light. Maybe there is a way around it. We are sure very far away from doing something like this. But someone is already thinking about it.
Excellent. Yeah, we have another one here.
Time travel.
Oh, time travel. That's something actually that they show in this Ant-Man films. And they find a workaround using quantum. I haven't heard anybody seriously talking about time travel, but I'm really interested in that.
We did do a demonstration with MPL last year where we put an atomic clock up on the, I think, 64th floor of 22 Bishopsgate. That's the second tallest building in London. And we left it up there for, I think, 6 weeks and then brought it back to MPL and compared it with the national timescale. And basically, it was a demonstration of Einstein's theory of relativity. So the higher up you go, the faster time goes. And so we worked out then the difference between the wages that somebody would have earned in their lifetime working on the ground floor of that building versus the wages they would earn on the 64th building. And I believe it was something like 0.00001 pence. So possibly even more zeros than that.
It's not worth the effort.
No, but, it's not fair. So,
No, yeah.
so that's, in a way, that demonstrates time travel, but it's really about how time appears to pass relative to another point. Yes.
Yeah.
That's as close as we have. We have another one at the back.
Yeah. Any work being done on the transporter room? So that
Yeah. On a holodeck.
Yeah, like, well, I know they can now teleport properties of light, let's say. So teleporting actual objects, I think it's not happening yet. But one thing they are teleporting for real is in institutes like this, they do teleport, let's say, quantum states. So they cannot transmit a state of something which is here somewhere else, just in terms of like its energy or no, but not actual particles. There are lots of questions around, like, if you teleport someone, it means that you decompose it and decompose it back again. Is it the same person? What happens to this question? So it's very controversial in a way.
Yeah.
About transporters, there is already automobile that is transporting into aircraft. I think in the Czech Republic they created this mechanical transporter, but they are struggling to obtain flying license because of regulations. So it's not possible.
Amazing. I think we had another, the man in the green shirt too.
You haven't mentioned the HAL 9000 computer in 2001, which is perhaps the most striking of all science fiction films. We don't seem to have got to that point yet. I mean, what do you think of the prospects of a really intelligent computer like that? Not a...
The topics like artificial intelligence together with quantum are really very emphasized these days. They talk a lot about AI and so on. And recently I'm not sure if that's true, but I was reading this article about some experiments where they gave some kind of fake data to AI, a very advanced AI, and those AIs were actually trying to manipulate the data in a way that wasn't predicted. So they kind of said, they were kind of telling the AI that we're about to shut them down, and the AI were using the data to avoid that. So I think eventually
I'm afraid I cannot do that, Hal.
No, yeah. We might get there, or very close to that at some point.
Yeah. Whereas at the moment, I feel like I have to ask my Alexa 6 or 7 times to turn off the lights, and it still doesn't.
Oh yeah.
So we're quite far away.
We are far away for sure. But, yeah.
I think we have time for one last question. If anyone has a burning question, yeah.
Is any science fiction actually get it right? Like you mentioned about Interstellar and films like that. Was there any good examples of science fiction?
I think Interstellar is a big collection of things they got right. One thing I was mentioning is the black hole. The fact that they land on a planet which is very close to the black hole, and then the gravity is so strong that time goes slower there is actually a real fact. So you mentioned that as well.
We basically demonstrated that on an extremely small scale because obviously 64 floors up is relatively a very small distance, but it's incredible that we could still see a difference of 40 nanoseconds, I think it was, which is like, to be able to measure that is what we're all about, really.
And then to me another good example would be The Martian. I love that film, and it's full of accuracies. Although it's fiction, but the way they portray the Mars and how it would be to be there, it's maybe they try to be as realistic as possible. Although radiation might be an issue that they didn't consider too much.
Cool. Okay, thanks so much, Allesio.
Thank you.
Have a round of applause. So our next speaker is John Turland with his talk, Mind the Gap. So we don't realise it, but we're actually making measurements all day, every day. So before we use any external devices to make a measurement like a ruler or a weighing scales, we use our senses to do things like measuring temperature, measuring distance. And then we also use things, as Allesio said, like our smartwatches to measure GPS and a whole host of other measurements that our smart devices and watches can give us. But how do we really know if we can trust a scales or a measuring tape? And is our oven really the temperature that it says that it is? So John Turland is one of our training managers, and he's going to take us through some of the inaccurate measurements that our phones make and make you think twice about how much we trust our senses and our tech. So yeah, please give it up for John.
Gee, thanks. Well, so a couple of years ago, my oldest son bought his first house, and he decided that he wanted to fix a leak in the bathroom. So you've got two blokes, my sort of size, squeezed into a very small room, trying to fix a hole in the floor that had rotted. I'll just wait for people to come in. too keen to go, sorry. I must apologise as well because you've had two beautiful accents on stage. And now you've got a Brummie who does not try and... I can't hide it. I've been trying for 50 odd years. So... Sorry? There is a large Irish population in Birmingham, yes. My wife, for one. So we got to the point in the bathroom where we had a hole to fix. Now, the tape measure was downstairs. Now, I've got quite old knees, so I thought, I'm not going down for that. I thought, I'm going to be a smart dad. I've got a measurement app on my phone. This is going to impress the kids. Zip, zip, measured. In the car, B&Q, comes back. I'm thinking, this is going to get me some kudos. I want to get some credit points. Do you think the piece of wood fitted the hole? Not a chance. So this took us down a bit of a hole, really, because get back. No, you're getting too excited. I went into discovery mode because it turns out with the app on the phone that we use, if you go left to right, you get a different answer to going right to left. If you stand and scan, you get a different result to scan and move. Take half a step back, you get a completely different set of numbers. So being an inquisitive sort of person, I start testing this out more and more. And I've started, for the younger people in the room, I've started doing this on school visits, and the kids now hate me because I've now got them questioning their phones for the first time ever. So you get quite a lot of variation, and hopefully, will you stop it? This is from a piece of software called Minitab, what we use. The bulk of the measurements are around. This is meant to be measuring a 1 metre length. The bulk of the measurements do come out around about a metre. Fantastic. But we've got quite a large spread, up to 1.5 metres on one measurement. Now, quite clearly, there was a breakdown there with the augmented reality between the lens and the processors and what have you. So we're at the point of where you question whether it's like when is it nearly good enough, or when is it accurate? So this is then, we're going to have a word with this clicker. So this morning, I measured a piece, and after this one, all come down to G14, and I'll show it you in action. I measured a 1 metre piece of wood, 94 centimetres, 6 centimetres short, 99, 102, 101. 4 measurements on the bounce, all completely different, with a range going from 94 up to 102, 8 centimetres. Difference. Same piece of wood, same phone, same idiot operator. There you go. And that was the one thing I did when I was doing it with my son. I thought, typical bloke, now all the women are going to go, yeah. I thought, are there instructions on the phone of how to use the app? No. So I got a free pass on that one because there was no instructions. So I'm now in a sort of chasing mode now. What else does this tell me that I believe blind? Okay? Now, come on, clicker, click for me. Right, now, as you can all see, I'm a gym bunny. Don't laugh, it's rude. So, this is from my phone this week. So, I've got 2 apps on my phone, pedometers. Monday, 7,906 steps on the one. Monday, 7,700. So, not a lot of difference, but a difference. Well, I'll go over there to click. This is just trying to get my steps up, isn't it? Up. Okay. So, where are we? Tuesday, 10,200. Tuesday, 7,000. 3,000 difference. Wednesday, 7,087. 7,300. Yesterday, 11,000. 8,600. Now, I'm believing this one, because this one's making me super fit and sexy, okay? Okay, that one is going to be deleted as soon as this presentation's finished. But on a serious note, we just take the data. We just go, oh, okay, that's fine. I mean, I'm not a gym bunny, you might have guessed that. But if that was my thing and I was using that to try and increase my fitness or lose weight or whatever, you would go with it. So the piece of wood is a bit annoying. This is a little bit more serious. Up. Stay there! Don't move! Anyone in this room using one of the diabetes things? It was actually because of seeing you walk, I thought that'll go on it. Potentially life-saving or life-threatening devices with our phone. Don't want to scare you, Jakob. Okay, don't panic, mate. Now, obviously, these devices have been licensed, tested, validated, verified. So if anyone's got one of these, please don't rush out and sue anyone. But we're increasing our dependence in our use of the phone and the artificial intelligence and the augmented reality that these devices now offer. Our watches can take your pulse and your blood pressure and. The phones are going to start expanding in their knowledge and their breadth of applications and bits they can connect to that help keep us going. And we're going to believe them. Are we going to believe them? Bearing in mind the stuff that I've just showed you on a very basic level. Guess on some stuff that we've got to believe them. Lessons learned. Lessons learned, my clicker don't work. Never trust a tech at face value. Biggest mistake. Especially when my kudos to my son had gone from there to, Dad, you're a blinking idiot. Why am I a blinking idiot, son? Because, he says, I teach people, I lead the apprentice, I teach apprentices. I did the one thing that I teach apprentices never do. I took one measurement and didn't verify it and validate it. One measurement. The thing I've spent 20 years telling young people not to do, I went and did it. Never answer the phone to your son when he's doing DIY. Say, thank you, sir, thank you, I'm with you, brother. Never do it. And always believe the results that you prefer on the app, okay? Okay? That, I believe, is the end. Hopefully it is the end. It is indeed the end. Thank you.
Amazing. I'm just going to try and flick this back. Yeah, here we go. Perfect. Right. Has anybody any questions for John?
No.
Anyone any DIY problems they would like John to come and fix?
Bloke over there will do it. He's on.
Yeah, absolutely. Any questions? Yeah, go on ahead.
When we get a tape measure from B&Q, other shops available, where do they get their measurements from? Or do they just go to...
Oh, that's a vile question to ask me. A vile question. You can actually get a tape measure calibrated to a UCAS standard, which I find bonkers. We do an exercise with young people where we get a series of tape measures from different, like you say, other retailers are available. And you can have up to sort of like 2.5 mil difference over like 3 meters when you pull them all out because of the way they printed them off. So there is a proper traceable UCAS standard traceable to international standards. But how good the one that you've bought is anyone's guess. I'd say it's more accurate than my phone though, whatever it is. But there is a international standard for it. It's very expensive to calibrate a tape measure, believe it or not.
So I was going to ask, does anyone actually come to NPL to do it, or?
I know of calibration houses that calibrate tape measures, and it's on their UCAS accreditation. And also, in the old days, pi tapes. Anyone heard of pi tapes? Someone said yes then. Yeah, thank you. It's just
My father used it.
see, it's just me and your dad's generation. That's just now I'm feeling really good. I've got dodgy knees on me wood, and now it's only 35. So a pi tape it measures around measures around bars, the circumference, to tell you what the diameter would be, because it's too big to measure with any other device. So these things can be calibrated. Fewer and fewer houses are doing them because there's fewer and fewer monies involved in doing it. But yeah, you can do it.
Another one I've often wondered about, John, is if I go for a run, if I log the run on my watch and then log using a separate app on my phone, one will come out as 5.02 kilometers, say, and then the other one might come out at 4.98, and that's a hell of a difference across.
Hell of a difference.
So what's going on there with GPS?
Now this is somewhere where I've just started to go. You see, because see back in the day. When I first got a phone, if I did the Find My Phone thing, it would go, it's somewhere in Birmingham. Okay? Now, it knows what room I'm in the house, because the way that we're using the computer technology and everything, obviously our measurement capabilities is exactly the same, but it's the way we can use that data and mix it. So, but there's no regulation to it. So whatever app provider is using whatever algorithms they want to use to put it out in whatever way they fancy. That's the thing with the steps thing. There is no standard. They can just do what they want, and you just go, okay. Because we're all turning into our teenage children. Okay. So, but that's essentially where it is. It's the difference in the algorithms in the app software that just churn out what you want to churn out.
Well, I'm going to take your advice then and
Take
the number I prefer.
the longest one, yeah.
Absolutely,
Yeah. Do that.
Another one is the likes of IKEA and other furniture shops are available. That when you are browsing on your phone, if you're taking a look at, say, a table around this size, you can augment the reality into your room and you can see what it will look like in the room. Now, my flat is 30 square meters in total, so it's about the size of a stage. And sometimes I have looked at furniture and I'm thinking, I mean, it might technically maybe fit, but you're not getting it A, through the door, and B, there'd be nowhere to actually move around. So you have to take it with a pinch of salt, I think, when you're looking at these things.
Indeed.
I wanted to ask you about tape measures as well, going back to 2 6 ago. When you buy a metal tape measure in B&Q or other places,
B&Q's doing well today, aren't they? They're getting some good press.
they're all over the place, aren't they? I mean, IKEA doesn't have the same, because it's paper, it doesn't have the same implement. But it's got that little hook on the end where you can hook it on. And that gives you a tolerance or something for a specific measurement. I read somewhere, but I can't remember what it is. What is that? It gives you about, I don't know, about an eighth of an inch or maybe a little bit less.
An eighth of an inch. We've been metric for how long?
Later on, you can have a look at the meter lab, but we don't have an inch lab.
Centimetres, not meters, but
I honestly don't know the answer to that question, unfortunately.
and it's to do with building. And
I wish I was clever enough to answer that question. I'm not that clever.
If I might, as far as I know, what that slidey bit on the end does, it means you can push it up against something to make a measurement,
Or you can pull it
on.
Right, okay.
And it gives you the difference between the hook onto the push.
Okay.
That would make sense because you're counteracting the thickness of the blade of the hook.
And the end of it is not actually flat, it's curved, so it probably might
people
be.
generally
an
don't
eighth
know
of an
that,
inch.
so then they can't measure accurately with it.
Yeah.
Or they could measure it to the nearest
And
centimetre.
fabric tape measures, which were
Flat.
what you had a lot of the time before they made them in plastic and things, stretched, so they were
Yeah.
never accurate either.
Just following on from that, if we want to be, I mean, just domestically accurate, are we better with a plastic tape, one of those that we track, than one of the foundations that were just making, the fabric one. Because I've always thought there must be a give and take.
The thing is,
I've
the fabric one can stretch.
Yeah.
So you can turn 30 centimetres into 31, whereas the plastic one won't stretch. So going through the uncertainty of measurement sort of question in my head, I'd say you've got less uncertainty with a plastic one than you have with a fabric one. But the plastic one's only good for measuring something straight. If you're measuring something that's got curve and context to it, you want the fabric one.
Or you get a piece of string and then you measure it.
And how long is a piece of string?
And how long's a piece of string? There we go.
No, it's double half its length. So we have a few more minutes left, and I know that the meter lab is one of our exhibits that's open today. So if you're interested in this and how we actually know what 1 meter is, because we don't rely on the standard block of metal anymore. We use lasers. So do you want to maybe chat a little bit about how they actually do that?
What, the meter?
Yeah.
You want me to do the meter?
Yeah.
Oh, are you all sitting down comfortably? Right, first of all, there was 2 hands shot up just.
Well, maybe you're going to cover it, but I just wonder whether laser measurements, the ones that estate agents use, who obviously don't really care about them,
Yeah.
trust them any more accurate than physical.
No, not at all. Just quicker and easier. Just quicker and easier. There was a hand up about someone else. Sorry, thought as well.
It was me, but it was a Thatcher's point about washing machine minutes and whether they are the same if you're watching the washing machine as not.
This comes back into this conversation earlier about slowing down time and time travel. So the bit about the meter, to pick that up. So most people think a meter is yay big. A meter. A meter is defined as how far light travels in a vacuum in 1/299,792,458 of a second. It's my job. It's what I do. Why 1/299,792,458 of a second? Because 299,792,458 metres per second is the speed of light. And that is never going to change. Doesn't matter what altitude you're at, what temperature you're at, anywhere in the world, the speed of light is the speed of light. So anyone can recreate a meter. All you need is a damn good stopwatch to get the 1/299,792, blah, 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 blah. So rather than being based on a physical artifact to compare against, now anyone in the world can make a meter with different levels of uncertainty of measurement because of the timer issue. But that is what a meter is, how far light travels in a vacuum in. You wasn't taking notes because none of you are coming back at me. So that's what a meter is. Yes, sir.
How old is the meter as a measurement then, if that's the case? I mean, it seems to me that it's probably 600 years old.
No, a meter has always been a meter. Since time began ever, a meter is a meter. What has changed is our level of accuracy that we can measure it to. So even in 1,000 years' time, a meter will be a meter.
But to answer the question of how old, it's 150 years this year.
It's 150 years.
We just signed the 150th anniversary of the meter convention. Some of our MPL colleagues were over in Paris, so it lines up with our 125th anniversary this year. So they were over in Paris, commemorating the 150th anniversary. Everybody agreeing that's a meter. Yeah, that's a meter. Yeah. So that's roughly how old it is.
Speed of light, then we thought, let's change our measurements of distance and base it on the speed of light.
The other way around. We decided what a meter was, and then we decided what it was in relation to the speed of light, rather than measuring it against an artifact. Is that correct, John?
That sounded really convincing.
It sounded good, didn't it?
Sounded good. Go with that.
Yeah.
Blag it. Fake it till you make it. What away.
Perfect. So we just have 2 minutes until our next talk, which is going to be about all things AI. Yes, we have one more question.
Just now. Because to work out that the speed of light is 299, 758, whatever.
Right, round of applause for that. That's not bad. Good man.
Then you worked out that calculation. You needed to have a physical meter in the first place, didn't you?
No.
I told you I was confused.
If you come down into my lab in G14, I can take you through.
I will come to you.
Okay. So it's about wavelengths of light, yeah, in the vacuum. So I get where you're coming from. I do get where you're coming from, but it's about the wavelengths of light.
So you can use the wavelengths to actually effectively the physical length drops out of the equation.
Having to rely on an object does, yeah.
Yes, having to rely on an artifact. There is now not one single SI unit. There are 7 base measurement units, SI units. Not one is based on a physical artifact now. They're all based on natural constants that cannot be changed. They will never change. So anyone can recreate any one of the 7 base units of measurement.
It's a little bit like exchange rates of currency, yeah. So if you're thinking about what €1 is in relation to £1, you didn't need to have the pound to know what the euro was. You just exchange what the rate is. So everybody agrees what the value of €1 is in places that use that currency. So it's kind of like we agreed what 1 metre was when we had a physical object, but we found a more accurate way to measure it because physical objects are subject to change, like John said, in relation to temperature, altitude, the material that they're actually made from, radioactive decay. All of these things affect how the measurement will change over time, whereas light is light is light. It's the same everywhere.
So going back to a previous person's question, isn't there an argument that a meter has changed? Originally, it was a physical thing. And now what you're saying, quite reasonably, is that actually it's defined as a number of wavelengths of light.
We're trying to say that it can never change again. Yeah.
Isn't that a different concept?
Fundamentally, the actual meter, in principle, as and always will be a meter. Our level of accuracy and precision that we can measure it to will increase. But a meter's not suddenly going to become 1.1 or 0.8 meters because of science. It's going to be a meter, but measured to 10 to the minus whatever of accuracies going forward.
So we just have to finish up just there on John's talk. But if you'd like to learn more about this, you can go and visit John in G14.
G14 Teaching Lab, the best place to be in this building.
So the teaching lab on your map, and then you can also find out lots more about this in the meter lab, which is also marked out on your maps. And that's all we have time for. So we have one more talk in this section, which is Valerie is going to come up and talk about AI. So if you'd like to head off, now is the time to do so. And we have some more people coming in. Thank you so much. Thank you. So for those who are sticking around, hands up if you think AI is going to take over the world. Oh, okay. We have a few takers. So to answer that question with some real science, we have Valerie Lavina, who is a principal scientist working in our data science and AI at MPL. And she's going to talk us through how AI works and what the real risks are and what remains firmly in the myths category. So we'll just give a minute or two for people to come in and out, and then I'll just give you a thumbs up to start.
You hear me over microphone? Yeah. Thank you.
Yeah.
Where is my back? Okay.
Yeah. So yeah, back. Back. There. Yeah.
Hello. Can we start? Okay. It's popular topic. I can understand it. Okay. Thank you. Good afternoon. So I'm a data scientist and mathematician by training, so I know very well how reliable are technologies, so I have only one slide. I will raise your hands if you ever communicated with chatbot of some customer service, like phone operator. Okay, some. And of those who were happy with the outcome, right? So we communicate with them and they ask your name and they are extremely polite, but they rarely resolve your problem, right? So actually this happens not only to all the kind of type of chatbots, but also to ChatGPT. There were recently examples when people were trying to resolve some problem and ChatGPT would, or other large language model, they go into circles trying to be more polite, more emotional, but effectively they don't resolve the issue. So what is the difference between thinking of a human and thinking of a computer software? Actually, I'm thinking about this all the time because I'm practicing AI. And when I get some outputs, I have to understand and analyze the result to interpret it because it's essential for my work. When human brain is approaching the problem and when ChatGPT or any software, AI software is approaching the problem, the solution can be the same, but what program is doing, it is kind of doing all kinds of combinatorics because computational capacity is enormous. All combinations like trying to figure out new combinations of chemicals, it will go at enormous lengths to understand all possible combinations. Humans, after trying 100 times, they will get bored, they will lose focus, they will start making mistakes, so it's impossible for us to think in the same way as computer software. But the result can be equivalent. It can be a discovery, right? So human brain is doing it as a quantum leap by sudden association, by previous memories. And what is extremely amazing is that energy consumption is very low. So it is estimated that energy that's required for human brain is about a light bulb. So this is the power, kind of 50 watt. And you can think about something, maybe 3 hours, and this is your outcome, you created something new. And computer will do it probably for several days, fully connected with multiple CPUs, GPUs, and consumption will not be that optimized because obviously they didn't go through thousands of years of evolution. The output is the same, but the question is whether our AI is actually intelligent. So when you are asking something from AI, what it is doing by construction, it's trying to find most from all the trained data that it grabbed from internet, from some databases. It tries to derive continuation of some sentence from its trained data, which is most probable. So very often when you read the output of AI text, it's kind of like average, right? Like something that you would expect to be written multiple times before. That's what they are doing. They are doing most probable derivation of very large training data. Human is trying to be creative. Human is trying to create something original that never existed before. So the difference between AI and the human thinking is motivation. So when you're trying to create something new as a human, you're motivated. Maybe you want to be a famous musician. Maybe you want to get very nice dinner, right? Maybe you want to find a very nice partner because they will be impressed with how smart you are. Computer, as you can imagine, they're not interested in that. They are written in such a way, I call it conditioning. When you write software, you say, if this, then that. So some software programmer who was actually writing the software, they have to put number of conditions to proceed with calculations or derivations. So when this condition is somehow wrong, it may happen that your output will be biased. Actually, it happened already to some experimental AI solutions when people trained on any internet data. There was Microsoft solution that was abandoned some years ago. They trained on any input data, and their output was racist, Nazi, whatever, because there was no conditioning. They didn't say, don't do this. If this happened, don't do this. So now people are learning because it's still infancy technology, and people are adding some anti-bias measures. They're adding some some restrictions. They're conditioning the software, but software is still without motivation. It's tasked to answer your question in a certain way with certain constraints. It will never decide to be a great musician or a great writer. It may perform very well, but it is following instruction of the software developer. So I would say that myth of taking over the world by AI is a real myth. And we should really believe that it is very unlikely that software itself will decide, okay, I'm taking all energy and you human will be disposed. No, it's unlikely. Unless some programmer, human, will have motivation to do it and he will write something like this. So it's not AI who is inventing this kind of evil idea. The real problem with AI at the moment is that because it's still kind of wild west in this area, direction in which it's developing may be not always optimal or very useful. When it is inventing new chemicals, it's wonderful. But when it starts writing poetry, if you look at this example, this is quotation from a writer who said that I would like to prefer AI to do my laundry rather than my writing. I think that this is a very important quotation because it says that this is probably not the right direction for AI to develop. Let it automate for us everything. Let it help us to be more comfortable, to focus on more important areas and to do something useful. And yet another real challenge with AI is that, as I said, it takes much more energy. So right now we're already reaching a stage when we spend almost 7–10% of our energy for data centers and AI. And this grows because people want bigger models. People want, it's already at the stage that large corporations, they have their dedicated power stations because they need CPUs and GPUs, and they may take one unit. GPU may take 1 kilowatt of energy, like a kettle. You switch it on and run it for 3 days. You get your monthly energy consumption in a flood. So it is something that we have to address rightly and help it develop into meaningful assistant for us as humans who still can be creative and delegate all the boring, tedious tasks, or those that are in harsh environment, to AI. So my conclusion, there are real myths about AI. You should not be scared about it, unless there is evil person behind it, really evil person who wants to take over the world, but not AI itself. And we have to be careful about what resources AI is taking and how it helps us, developing it in the right, useful direction for us. Thank you.
Thanks so much, Valerie. Have we any questions for Valerie about AI? Oh, we have two already. Yes, someone in the back here.
Do you think our government is doing enough to make sure that the people that are developing AI are using it for good, the right way?
It's not only our government, it's also across the EU. There is so-called EU AI Act, European Union. And also, I think it's globally, because at this stage, people already know that there may be biases and there may be distortions of development. Let's say 5-7 years ago, it was more Wild West in this area. Now it's more regulated. But at the same time, we have to keep it free enough not to restrict innovation, because it's also very important to let people develop whatever can be novel and interesting. But I think the scale of implementation is still not that global, and it's not a kind of unruly stage. I don't think there is a danger in that context at the moment. We already passed more dangerous period. Of course, they may become more advanced. Many people express concern about their powerful, that is growing very quickly. But as you see, talking to these bots, even most advanced LLMs, they're still AI, so it's artificial, but not non-AI. I would say they're not particularly intelligent at the moment. They pass Turing test. That means that they resemble human, but resembling a human is not the same as being a human. We are still smarter. Don't worry.
My favorite is the customer service bots that say, "Did you know that you could find this on our website?" I was like, "Well, I couldn't, and that's why I'm here."
I usually type, "I want to speak to human. I want to speak to human," until they transfer me.
Yes. We had another question here. Yeah.
It was the same one actually. It's just how we can safeguard against an evil human, not evil AI.
So at the moment there is lots of kind of technical activities in the area of standardization. I participate in British, European and international panels on standardization of AI. And there are multiple documents that are prescribing what to do and what not to do, how to handle the data. Actually, if you are curious, you can go, it's called ISA SC42 Artificial Intelligence Committee, and there is a working program there, dozens of standards in development. And large corporations actually participate in developing them. Microsoft, Google, they send representatives. So it is a collegial effort. They are not trying to escape. They try to comply with it because they want to sell their products, obviously. So I think it is right now in healthy stage, I would say.
We hear a lot of things as well about AI and the environment. So particularly like the likes of ChatGPT or other LLMs are available. That if you put a query into one, say something that is relatively trivial, so you think, oh, I'd really like to buy a new garden shed. Please, can you compare 6 different varieties of garden shed with this budget? Yeah, it's a pretty trivial thing, but it'll do a pretty good job.
Mm-hmm.
But people being a little bit concerned about how much water that uses up, how much carbon emissions that contributes to, just for something that you could spend a little bit of time yourself researching. Do you know anything about that, or kind of how much of that is true, or how much of that is a myth?
So if you do simple Google search, or for the same you run ChatGPT inquiry, you will get kind of give me image of hand from Google and created by ChatGPT. It's about 10 times bigger energy consumption, and that is for power, and it is for fresh water, which is cooling data centers. So I would, if it is something simple, I would recommend always to go for Google search. But now Google is implementing their own model, unfortunately. So they are kind of speeding it up to be in line with other corporations. In principle, I can, because recently I participated in developing European standard Sensenelec. It is called technical report 18145. So it's environmentally sustainable AI. It provides methodology for calculating carbon footprint of any AI solution. So it takes into account how many GPUs, CPUs, memory units multiplies by duration, and it takes real-time carbon footprint of the national grid. So effectively, you, with resolution 5 minutes, can extract almost real-time data of fuel mix of the national grids. How many power stations are running at the moment when you are running UAI? And by this, you will know carbon intensity, about 200 grams per kilowatt hour. And then you can derive explicit carbon footprint of your solution during half an hour or 1 hour that you run it. So it's quantifiable, straightforward.
Very straightforward.
Well, I can approximately tell you.
Now, the exam will start in 2 minutes.
Number of kilowatt hour.
So we have to leave it there, I'm afraid. But if you take a look at your maps, you will see that there is an AI activity, and you can go and chat more to some of our scientists about artificial intelligence throughout the day if you want to have a look around the labs. We have a break just now for our speakers, and the next set of talks starts at 3 o'clock. But please do go and explore our labs. We have more than 55 exhibits open today, so there's something for everybody. And thanks so much for your time.
And I'm available in the interval.
Hello, everybody. It's great to see a packed auditorium for our talks program, How Long is a Piece of String? So welcome to MPL Open Day. How's your day been so far? Come on. We're delighted to be welcoming so many of you to the MPL site today to have a look around all of our labs. We have more than 55 different exhibits for you to have a look around today. So please do check out the map and make sure you chat to our scientists about all of our science up close. Just a few practical notes before we kick off. If you're hard of hearing, it might help you if you'd like to join our live stream, so you can find out how to do that on your map. It'll just give you access to the auto-generated captions on the YouTube live stream, so if you keep your phone on silent, if that's something that might help you. The exits to the auditorium are behind you, so when you're leaving the auditorium after this talk or after a couple of the talks, just make sure to leave through that door. Our lovely volunteers will guide you. And in the event of a fire, you can use both of these doors as a fire escape and also this fire door here. And if you wouldn't mind just having a look at your phones and watches and various other smart devices and just making sure they're on silent, that would be super helpful if you just take a minute to do that. So, on to the business of the day. MPL was founded in the year 1900 for standardizing and verifying instruments and for testing materials and the determination of physical constants. And since 1900, we have worked in every branch of physics and across all kinds of science and engineering in light, electricity, magnetism, radio communication, aeronautics, health, manufacturing, ship design, and much, much, much more. We have been at the forefront of some of the most amazing and impactful innovations in the world, from the development of the internet to improved cancer treatments, and the invention of radar and the development of atomic timekeeping, which you can actually find out a bit more about just outside the auditorium here if you'd like to take a look at an atomic clock. And at the very beginning of MPL, the then Prince of Wales gave a speech in which he said that MPL's purpose would be to bring scientific knowledge to bear practically upon our everyday industrial and commercial life, to break down the barrier between theory and practice and effect a union between science and commerce. And hopefully, as you have a look around today, you'll see some evidence of that. And it's incredible to be here as part of an organization that is still delivering on that mission 125 years later. So thank you for being with us to celebrate our anniversary. This is the second edition of How Long is a Piece of String Live, which is our talks program. Our first event was in March, and that was all about the science of sports. And today the theme is all about myth-busting with metrology. And you'll be hearing about all kinds of things from orcas. Earlier on we had phone measurement apps. And later on today you'll be hearing about the ocean levels rising and much, much more. And so, just bear with me 1 second, because I've got my cards in the wrong order. We have our grads group who are going to talk about whether the world is as safe as it seems, so measuring the likelihood of life's mishaps. We have a tinfoil hat that's just been placed on somebody in the first row here, which might give you a hint as to some of the topics that are coming up. So fear is a basic instinct, and sometimes our perception of danger is linked to scale in a bit of a weird way. So we assume that bigger means more dangerous, but that's not always the case. So our fabulous group of graduate scientists are going to be talking about killer whales, 5G, and whether a kilo of feathers really is the same as a kilo of steel. So please welcome, Daniel is going to speak first, and there'll be 4 graduate scientists speaking, so please give them a big round of applause.
Hello, everyone. Let's put this off for the talk. This is fine, don't worry. I have 5 minutes to talk to you about 5G. So I need to cast your minds back to 5 years ago. We were deep in the midst of the coronavirus pandemic. People were linking 5G to coronavirus as 5G was becoming a new technology. Towers were being burnt in Manchester, Birmingham, Merseyside. But were the conspiracy theorists right? Is 5G really dangerous? Well, today we're going to be asking those questions with science. The answer of is 5G linked to the coronavirus is a very simple one. No. Coronavirus is spread through air particles and droplets, not your mobile phone. But some people were saying that the coronavirus may have developed in Wuhan due to the presence of 5G in the area. But when the pandemic first started, the 5G network in Wuhan wasn't even fully developed. But to answer whether 5G is more dangerous in a general sense, we're going to have to look at what 5G actually means. So 5G just stands for 5th generation. It's the 5th generation of cellular network technology, which is just how our phones communicate. So an area is divided up into cells, with each cell being served by a cellular base tower. And so any device within that cell, so your phones, for example, would communicate to these towers via radio waves. Now, radio waves, like many things, exist on a spectrum. In this case, it's the wonderful electromagnetic spectrum. But we'll get to that a little bit later. For now, time to do a little bit of maths. So bear with me. We know the speed of light, and we know that it's constant in a vacuum. We also know that speed is distance over time. In waves, this is the frequency multiplied by the wavelength. But that speed is the speed of light, so it has to remain constant. There's this sort of push-pull between the frequency and the wavelength. As one increases, the other has to decrease. So if we jump back to our electromagnetic spectrum for a second, ooh, are we going to jump back? We'll see. There we go. We see on the left-hand side, we have really high wavelengths, but really small frequencies. On the other side, we have really small wavelengths, but really high frequencies. And these are gamma rays, which are ionizing radiation. That means they can harm the DNA in cells and cause mutations, which can cause cancer. So the gamma rays are really dangerous, but they're dangerous because they have high energy. So, there's a reminder of the speed again. Let's jump through to, hopefully, the energy equations. But if you can't get there we go. The energy, E equals hf. H is Planck's constant, one of the physical constants Joanne was talking about earlier. And F is our frequency from before. But for radio waves, we have a really high wavelength, which means a smaller frequency and thus a smaller energy. So theoretically, they should be less dangerous. But wait, there's also ultraviolet on there, UV. And we know that causes skin cancer, sunburns. There's also microwaves. Microwaves at home heat up food. That's through the interaction with water particles. And we're made of water, so microwaves can also be dangerous. What about radio waves? Why aren't they dangerous? Well, the answer is all to do with power. If you have a microwave at home, it would have a number on it about like 800, 900, or even 1,000. And that's the number of watts it has on it. Watts being a unit of power. And all that power is concentrated in a really tiny area inside the microwave. Your phone, on the other hand, is limited to only producing a couple of watts. But if you have really, really good connection, it's going to be down to just a few milliwatts. But with phones being so prevalent in today's society, there's been a lot of scientific research conducted on the topic. One of the more sort of infamous and controversial studies was conducted in 2018 and featured a 10-year-long study into the effects of radio waves on rats. If you jump through, the study said that there is clear evidence that specifically male rats exposed to high doses of radio frequency radiation experienced an increase in cancerous heart tumours. However, and this is a big however, one of the senior scientists on the project said that the exposures used in these studies cannot be directly compared to the exposure that humans experience when using cell phones. And the rats were exposed to 9 hours a day with radiation across their entire bodies for much higher doses than any human would receive. Also, the rats during the project also experienced longer lifetimes than those in the test studies. But this is just one study, and we had to do a lot more research to conclude anything empirically. So in 2020, America's FDA, the Food and Drug Administration, conducted a bit of research into looking at 125 articles that linked radio waves with cancer, including actually that rat study from before. And across these 125 articles, they concluded that there is no correlation between the two. So what does that mean for us? Is 5G dangerous? Can our phones really kill us? Well, so far, scientists haven't found any evidence that they can. But this is what science is for, is to keep asking the questions, to keep doing the research. And right now I'm going to hand over to one of our other excellent scientists, Hannah, who's going to give another talk to show you that the world isn't as dangerous as you first may think.
I'm assuming that you can all hear me. I can hear myself, so the answer will be yes. So, oh no. There we go, cool. So my talk is on the dose makes the poison. And this is basically, this will make sense in a second. I realize I've just got a banana. But basically, the dose makes the poison means that anything in very, very large quantities can be harmful. And an example of this is a banana. Okay, but before anyone freaks out, it would take eating 100 million bananas in a 2-week period to get a fatal dose of radiation. That is over 7 million bananas a day, which is just under 300,000 bananas every hour for 24 hours, which, I don't know about you, I couldn't do it. But radiation is, I don't want to say a problem, but it can be scary. Some people can be scared of it. And some things increase our exposure to radiation. And 2 of those things that I'm going to talk about are flights and X-rays. So, an average flight between London and New York City is about 7.5 hours. And that would be the same as eating 400 bananas. And then that would also be, oh, I've moved on. Oh, the same as taking 250,000 flights between London and New York City. And if you wanted to look up how many flights there were between those 2 places in a week, it's 30. So physically you wouldn't be able to do it. And then the next one is X-rays. So I'm speaking about 2 different types of X-rays. So there's dental X-rays, which is the thing that they do at the dentist where they put that thing in your mouth and then they leave the room, which seems terrifying, but it's actually only the same as eating 50 bananas. So it's really not that much, which is, you know, the same as having 2 million of those dental X-rays is the same as the fatal dose of radiation. I'm also going to put the banana down. I'm just waving it around now. And then chest X-rays. So there is a range of how many bananas a chest X-ray would be. So I've just gone with the biggest one, which was 1,000. Again, that's not very many bananas. And so it would be 100,000 chest X-rays to get you to the fatal dose of radiation. And all of that is within 2 weeks. So it's very much not really possible. Oh no! Spoiler. Oh. Okay, and the next thing I'm going to talk about is medicine and the therapeutic range. I promise it's vaguely related. Basically, in medicine, there is a thing called the therapeutic range. This is basically the concentrations that the active ingredient in the medicine needs to be within for you to be safe and not have too many adverse side effects, because annoyingly with medicine, you can't tell it where to go. It doesn't have a brain, you can't tell it, I have a headache, go to my head. So medicine or the active ingredient just binds to receptors, and sometimes it can bind to too many. That's if it's in the harmful range. So all medicine that you have in your house is within this therapeutic range where it is effective and will do positive things for you, but isn't going to cause too many adverse side effects, which is good. We don't want it to do that. So yes, all this to say is the dose makes the poison just means that too much of anything can be bad for you. And now I'm going to pass to the next grad who's going to talk about stats using animals.
Thank you, Hannah. Just want to check I can be heard. Brilliant. So, fears. They're our body's subconscious reaction to danger. So can I get a quick show of hands in the room? Who in here is scared of spiders? What about scared of sharks? What about scared of snakes? So yeah, these creatures can seem very dangerous and feel very scary. But is it correct? Is this fear perhaps misplaced? So today, I'm going to be talking to you about the deadliness of these different animals when it comes to humans. So we're going to be looking at the average number of human deaths per year for each of the animals we look at. And I'm going to be using this as a means of showing how the presentation of statistics is important. So, to start off with, as you can imagine, there are millions of creatures that have never been recorded to kill a human. But I chose one that I thought was particularly interesting, and that is the orca, or the killer whale, which has never been recorded to kill a human outside of captivity. So in the wild, it's never been recorded to kill a human. And on this same wavelength, there are millions of creatures which kill very few humans per year. And I've chosen two, which I think we've identified, can be quite scary. And those are sharks. Yes, sharks and spiders. So on a yearly basis, there are typically between 50 and 80 shark attacks per year. And these will only result in between 5 and 8 deaths, which means that if we look at this as a percentage, in terms of the interactions with sharks, we will have between 6 and 16% of fatal interactions. When we look at things like spiders, the interactions with these are far more common. People will be bitten by spiders all the time and often won't even notice that they've been bitten. And so this is a way of showing that the number of interactions, although they have a similar number of deaths, the number of interactions are very much different, and hence the dangers of these creatures can be perceived in different ways. Now, we can move on to the middling range, and we'll look at both lions and deer. Now, this seems counterintuitive. You know, lions are these apex predators, the king of the jungle, and deer will run away if you break a twig in Bushy Park. But again, this comes down to the number of interactions we have with them. We'll have millions of interactions with deer yearly, and most of these will not involve any injury at all. But if we have an interaction with lions, these are going to be few and far between, and let's be honest, they typically won't end well. So this is a good point to kind of take a step back and look at how I've presented this data so far. If someone was to come and look at this data, you might say, oh, well, deer are far more dangerous than sharks. You know, they kill far more people per year. And that could be the response that you come out of this presentation with. But as a matter of fact, when you think about it in more depth, actually, we interact with deer so many times that the percentage of fatal interactions or dangers of these deer are actually pretty low. But actually, the percentage of sharks where it could be dangerous or be fatal are actually pretty high. So it's just important to think about, when you're looking at these statistics, what have they been designed to show? Statistics are a powerful tool to push different ideas. So it's important to think about what information has been shown, what information has been omitted, and why that might have been the case. In the interest of time, I'm going to skip over crocodiles and scorpions and move straight over to the top 4. So to start the top 4, we have dogs. Why is it going so far? Where's it going? Yes, it is my slides that have lagged out the rest of the presentation.
Yeah, you can see 60,000 there. I think it's actually 61,000 transitions.
Yes, yeah. So I'll just continue as I'm going, and I'm sure it will catch up at some point. So when we look at dogs, these have between, I say, 30 and 60,000 deaths per year, but these are not your average domesticated dogs. These are particularly wild, stray, and rabid dogs. I'm not suggesting that you should think of my dog there as anything other than cute. Now, when we look at number 3, it's actually an interesting contender, which I was quite surprised at, and that's the freshwater snail. Now, the freshwater snail itself isn't innately deadly, but it carries a parasitic disease, which, when introduced into a water supply and ingested, can cause things like anemia and death. Now, this means that you should be particularly careful when drinking unfiltered or unchlorinated water in parts of Africa, Asia, South America, the Caribbean, and the Middle East. Now, at number 2, we have the snake. Now, the snake is very versatile to different climates, and that means it can be found on all continents apart from Antarctica. This, combined with the fact that they typically hunt larger prey than some of the other animals, means it's particularly capable of causing damage to humans. At number 1, as I'm sure you saw earlier when the slides went on, is the mosquito, if it will load. Now, mosquitoes massively swamp the other animals when it comes to the number of human deaths. But again, just like the freshwater snail, mosquitoes themselves aren't innately deadly. They often carry diseases such as malaria and Zika virus. And this, combined with the fact that mosquitoes are particularly common and particularly small makes them very difficult to avoid, and this is why they can be quite deadly. Now, we've got the whole list that I've chosen to include, and it's important, and we've got another point of statistics that we can reflect upon, and that is how the statistics are relevant. So looking at these statistics, these are worldwide statistics, you might think, oh no, I've got to be scared of the mosquitoes in my house. But as a matter of fact, in the UK, you're very unlikely to be eaten by a lion. You're very unlikely to catch a disease from a mosquito. As a matter of fact, the only venomous snake in the UK is the adder, and the most deadly of the spiders is the false widow. So it brings about the question of how you want to make sure that the statistics that you're thinking about are relevant to your current situation. So in the UK, what is the most deadly animal? And sources will find this value quite hard to quantify. But sources online seem to agree that one of, if not the, most deadly animal in the UK is... Ooh, the cow. So BBC Science Focus attributes 22 deaths to cattle-related injuries between 2015 and 2020, and the Health and Safety Executive attributes 8 deaths to cattle-related injuries between 2022 and 2023. So, to conclude, statistics are very important when trying to think about, when trying to portray different ideas. And it's important to think about why the statistics have been presented, what they are showing and what they aren't showing, and how they are relevant. So taking today's presentation, we might look at that, that timeline before, the timeline of deaths, and say, well, the apex predators seem to be less deadly to humans than the smaller creatures which are harder to avoid. Now, does that mean that we shouldn't be scared of these apex predators? Well, I would say no, because if you were face to face with a lion or a snake, it's most likely going to end far worse than if you're face to face with a deer. And so, actually, our instincts are indeed correct before looking at these statistics. And it's just when you think about it and get the full picture of the information, that is when you can start to make your own judgments. And to talk again about how our instincts are correct before learning the science, I will pass you over to our graduate, Callum.
Thank you, Jack. Just testing that the mic is working. I'm actually going to have to pop it down to grab some props. Bear with me. Maybe I can do it like that. Nice. Okay, so this next part is focused a little bit more around how sometimes your intuition and your instincts can be right, and to trust your gut sometimes. Will the slides work for me? Probably not. Here we go. So this is inspired by a sketch from a Scottish comedian called Limmy, in which he is perplexed at the fact that a kilogram of steel is the same weight as a kilogram of feathers, because steel's heavier than feathers. And whilst that's not quite the case, there's still a lot of reasons that you would rather have a pillow drop on your head than metal. So what I've got here is a pillow that weighs roughly 800 grams, and then a pillowcase full of metal pieces that also weighs around about 800 grams. So show of hands, who would rather have the pillow fall on their head? Pretty conclusive, okay. But if they both weigh the same, why is that the case? So we'll start with basic physics, which is they both have the same mass, and that's the amount of matter that's in the object. However, it's how that mass is spread out that makes the difference. So the metal is hard, it's dense, and that's the key word there, the density. The pillow is big, fluffy, it catches a lot of air. The metal is hard and dense, and the density is what makes the difference, as that's what hurts when it hits you, because it will apply a greater force to a smaller area. So let's see, there you go. The density is the mass in a given volume, and as you can see from the kind of arrows there, you've got the force being applied from a smaller surface area compared to the pillow, which is pretty straightforward. Bear with me. There we go. And part of what comes from the density is the larger surface area, and involved in this is air resistance. So air resistance is the drag that comes from the air when you drop two objects, And as you can see, well, maybe you can't, as you can see with the pillow, it's big, it's fluffy, it catches a lot of air when it falls, whereas the metal is, like I said, compact, it falls faster and it hits harder. This is part of a concept called terminal velocity, which is the maximum speed that something can reach when it's falling. So I'm wondering if I can do this here. Bear with me. I'm really hoping I don't break the floor when I do this. If I was to drop these, it's probably too small of a distance to see, but I bet that the metal would have landed first, and that's because it has a lower air resistance. And like I said, once that reaches the terminal velocity of the metal will be higher. So if it was to drop from the same point, when it hits your head, it's going to be faster, it's going to hurt more, which is obviously a reason that you would rather choose the pillow. We can also talk then about the impact force, as you can see from this equation in front of you. Oh, not that equation. The equation before. So when we've got the mass remaining the same, what we will look at is the impact velocity, which is what I mentioned there, and the stopping time. Now, the stopping time, the larger the stopping time is, the less the force will be. And that brings us on to another concept from physics, which is impulse, which is the next equation. An impulse is how long a force is applied for. So with the pillow, it's soft, it's squishy, takes longer to compress, whereas the metal, the stopping impact is much shorter, and that means that the force is applied over a shorter period and it hurts a little bit more than the pillow. So can we relate density to the force that's being applied? Yes. We can see that when you drop the pillow, it catches more air, so it falls slower. When you drop the metal, the force is applied on a smaller area, so it hurts more. And the pillow has more, there's no other slide. The pillow has more give in it, so the impact time is longer and that force is spread out, not over space, but also over time. So whilst you would agree that saying that a kilogram of steel is heavier than a kilogram of feathers is not true, you would still want to choose the pillow over the steel being dropped on your head for these reasons. Thank you very much.
Thank you to our 4 fabulous grads. We're a little bit tight on time, but I think we have time for just 1 or 2 questions from the audience for our grads. Anybody have any burning questions that they'd like to ask? Yeah, we have one here.
What's the source of radiation when you're flying?
What's the source of radiation when you're flying?
It's cosmic rays.
And if you take a look at our, I think we have a copy here actually, our little book of Big Impact, which is, you can find it around site in a few different labs today, and it's also available in our gift shop. We have a couple of bits in here about theoretically how much more radiation somebody is exposed to if they work in the aviation industry. So somebody who has to take flights as part of their living, whether that's hosts on an airplane or pilots, they're exposed to a little bit more, but it's not enough to actually cause that just goes to Hannah's point of you would really need to take a tremendous amount of flights for it to really make an impact or bring you closer to that fatal dose. I'm afraid we have to leave it there just because we're running a little bit behind time, but thank you so much for your attention. If you're leaving after this talk, please just head out that door, and just one more round of applause for our grads. I think we are ready to go. Sorry, I forgot to give a signal to the to the people at the back. Welcome, everybody. Thank you for joining us for MPL Open Day. Just really quickly before we kick off, the fire exits are the 2 doors behind you and this door here. And if you wouldn't mind just checking your phones are on silent before we kick off, that would be great. We've had a fantastic talks program today, and the talks are now also streaming in G14 and in reception downstairs. So apologies to anybody who is disappointed and couldn't make it in earlier on. But we now have the tech up and running to show it around site. Next up, we have a talk about measuring the chemistry of life. So when we have an ache or a pain and we take something like paracetamol, how does the drug know where to go? And we touched on this with Hannah's talk earlier on. And then what about drugs for much more serious illnesses like cancer? So Ian Gilmore is a senior MPL fellow working on all sorts of amazing science at MPL that all ladders up to the one big idea of measuring the chemistry of life. And he'll talk about therapies, how they're made, and how we measure the different ways that they work in the body. So please welcome Ian.
It's really great to see everybody here. The UK is absolutely amazing at the life sciences, and you all know about the Nobel Prize for Crick and Watson, but we've probably per capita had more Nobel Prizes in the life sciences than any other country. And because of this really vibrant science base, it means we've grown really world-class pharmaceutical companies and biomedical companies that not only make us live longer, live better lives, also return a massive amount of investment to the UK, one of the biggest contributions to our GDP, and employ hundreds of thousands of people. So it's very, very important. And the work of me and my group is about measuring the chemistry of life. And I work a lot with the pharmaceutical industry. I'll tell you a little bit more about that, in that, I don't know if you know, but it takes about 10 years to go from the original sort of idea of a particular drug molecule, this is a typical kind of drug molecule, from those early days of knowing it has some biological effect, right through to a medicine that you can take. It takes around 10 years. And it takes billions of pounds of investment to do that. So there's a huge amount of work that goes on, and I'll talk a little bit about more, to try and optimize all of that so we can get the drugs sooner and also make them more efficacious, so we can make them more effective to people. And also, I work a lot with the leading biomedical researchers. So we're very lucky in the UK, as I said, to have a very strong academic base. I particularly work a lot with the Francis Crick Institute, which is one of the biggest biomedical research institutes in the world. And so a lot of my research is around the cell. So I don't know how many people are kind of familiar with the cells. I'm a physicist by background, but over the last 10 years or so, I've moved more and more into biology. And I still amazed by the cell. So here is a cell. I can pass it around. I don't know if anyone wants to have a look around and move those around. So that's about 5,000 times the scale of a normal human or animal cell. And in the center there is a nucleus, as you'll know, where the DNA is. That's the information that codifies basically everything that then goes on with our bodies. So this is your DNA and the genetics. They then do something called the RNA, which is the transcriptome. So those are the kinds, they send the messages to the other parts of the cell, which then make the proteins. And the proteins are then the things, the machinery within the cell that gets things done. It makes the different parts of the cell. It does the different things in the body. So that's something called proteomics. And then the proteins and everything that's going on in the cell is creating information, really. It's essentially a form of information. This is the chemistry of life. It's the metabolism. So you will all sort of kind of know, some people have a higher metabolic rate than others. So that's the way you process the chemistry that's going on in your cell. But it's amazingly complicated. So our body's, of course, mostly made of water, right? And the cell is mostly made of water. So the first job it's got to do is contain the stuff inside the cell and stop it just going blur everywhere. And it does that very cleverly, just like you see when you're doing the washing up, if you have a bit of oil that goes onto on the nice in your nice sink in the water, you'll feel it beads up, of course, because it's hydrophobic and the water's hydrophilic. So the cell is made out of lipid membrane. These are molecules which are very much like a fat. It's a long chain of carbon atoms, but they have a little polar head group in. So the polar head group part is happy to be in the water, and the long chain part doesn't like to be in the water at all, so it sticks out. And they automatically, if you drop these kinds of lipids into water, they immediately assemble a sphere. It's very, very clever. It's incredible, really. And if you go down to the engineering biology lab in Module 8, you'll see the amazing work that Max Riadnoff and his team are doing, engineering these kinds of structures from first principles. So we have this membrane. If, as we talked earlier, if we want to get a drug into that cell, not only do we need to deliver it to the right cell in the body, but we've got to get it through that membrane. And that membrane is, as you know now, is hydrophobic. It wants to expel things that are water-like. So this is a typical kind of drug that we might want to look at. This is a drug called amiodarone. It's a drug used in arrhythmia. If we want to get the drugs into the body, we normally take it through a medicine, a tablet, and then the drug has got to be soluble in some way. If it's not soluble, then it'll be like dust, and we won't be able to get it actually into the body and around to the affected part of the body. So that means it's got to be kind of polar. It's got to be happy to be in the water. So once the drug then gets towards our cell membrane, it then sees this layer here, which is hydrophobic. This molecule's hydrophilic, and it won't go in. So a lot of work goes on in the pharmaceutical industry to try and tailor the properties of this molecule. We can see these red things are oxygen atoms, so they're going to make it kind of more hydrophilic. These are, unusually, these are iodine atoms. The black things here are carbon. The loss of carbon in there usually makes it hydrophobic. So a big challenge for the pharmaceutical company is to design the drug so it has the right biological effect when it gets to, usually these things interact with a protein molecule, and that protein molecule then is disrupted in some way, and that then is used to treat the disease. But if we don't get it into the cell, that's the problem. So if you see, for example, a good example of this is, for example, the messenger RNA vaccine that was developed by Moderna that we all knew from the COVID times. The RNA is a very polar molecule, so that won't go into the cell at all. But it's actually delivered in a lipid vesicle. The lipid vesicle surrounds it with something which is really hydrophobic, and then that will come towards the cell membrane, and then it will go in towards the cell. So this is really starts to be a lot of very fascinating processes that go on. So I just wanted to start off with, will it come? No? Yeah. One more. Whoa, okay. Yeah, so this is a quote from a Nobel Prize winner, Sidney Brenner, who I find really inspiring. And what he said is, what we really need to learn from this is that mathematics is the art of the pure, physics is the art of the optimal, and biology is the art of whatever wins will survive. And this is exactly what I found. Biology is so complicated because of evolution. So what do we really mean by life? So one of the sort of tests for life is, can it evolve? And can it sustain itself in its own environment? So yeah, the other reason I really like this talk, this quote, is because it brings together kind of the key things that we need as scientists to be able to make progress in this field. So in my group, we bring together people in mathematics, people in physics, people in biology, to be able to look inside the cell. So everyone's got the cell now. If you see inside that now, let's say we've managed to get our drug molecule into that cell. It's only a few microns in size. And if I'm now trying as a pharmaceutical company, I want to know, have I got enough of the drug into that cell? Where has it ended up in that cell? That's where measurement becomes really key, because if they can have that information, they can then see if that drug is going to be effective. And that's exactly what we do here at MPL. And the other things that we need to take care of is, remember, we have this 10-year timeline. What if that molecule is actually going to the wrong cells and causing a problem? So this molecule here, amiodarone, is actually well known. Although it's a very effective drug, it does go into macrophage cells and that starts to have a side effect. And then we can, using the techniques that my group here at MPL are developing, we can see into those cells and see what's happening. And that's really important information for the companies developing the drugs, because they can then tailor these designs to be able to optimize where the drug goes to particular cell types using better delivery mechanisms. The other thing is that inside the cell, there's lots of different compartments called organelles. And if the drug goes into one of those organelles, this could also be a big problem. So the mitochondria, as you probably heard, that's about a micron size, looks like a bacteria inside the cell, like a sausage shape. And that's the energy factory of the cell. If drugs get in there, that can really be a very big problem and can cause the cell then to die. And obviously you don't want that. So looking for very early signs of the drug going to the wrong place can then save 8 years of research that in the end would be wasted. Likewise, there's the lysosome is another part of the cell. This is where this drug often can end up in. So if we can spot all these things earlier, we can help make better drugs. But it's actually very difficult to see. Can you imagine the chemistry in the cell? There are thousands and thousands of different molecules. And we need to be able to sort of look into that cell, which is a tiny amount of liquid, and identify what exactly all those molecules are, where they are, and how they interact with each other. And that's exactly what we do at MPL. And if you, my lab is currently open in Module 8. And if you go over there, you can see the imaging technology that we invented here at MPL. And it's now in use all the way around the world. This it's actually really the most powerful molecular imaging technique that you can get. And we are using it also to sort of look at fundamental biology. So I think this is just how this kind of thing works. So we normally take something like a tissue sample here, or it could just be a single cell that we can do that. And oh dear, this has got a build-in. Let me just build it all the way through. Okay, yeah. So we use, in our case, we use something called an ion beam, which is a very focused beam of ions. It hits the sample surface. Every time it hits the sample surface, it liberates molecules that go into the gas phase. So these molecules could be the drug molecules that are in the tissue. It could be the lipids from this lipid membrane. It could be the protein fragments. Or it could be the metabolites, which tell us about how healthy the cell is, or this information changes that are going on. All of that then goes into something called a mass spectrometer, which basically just separates out all of this material coming off by their mass to charge ratio. And then once that's in the computer, we can select particular peaks, and from that we can then reconstruct an image. And the amazing things that we do at MPL with this is that we're pushing the limits of the resolution. So it's a bit like, you've heard of like the Heisenberg uncertainty principle, where you either know something's momentum really well, or you know its position really well. In biology, we have something very similar. So we can either know its identity really well, but then we have no idea where it is. So to do that, we have to use big techniques like nuclear magnetic resonance. Or we can use techniques which allow us to go to very high resolution. You might have heard of electron microscopy, but then we've got no idea what it is anymore. So it becomes a real problem. So in my group, what we've done is we've really pushed the boundaries of being able to know what it is and where it is simultaneously. And that's really been a big breakthrough, not only in biology, actually, but generally in the life sciences and in advanced manufacturing. Let's see if I can go to the next. One more. Yeah, and at MPL, we have the National Centre of Excellence in Mass Spectrometry Imaging, which is one of the world's largest centres. We have a whole range of these different imaging capabilities. So in Module 8 and in Module 7, you can go and see the labs there and all the different things that we do. And one of the methods, you can actually, it's used in surgery. So as the surgeon is cutting through, for example, some cancer tissue, it gets a readout into the mass spectrometer looking at the metabolism of the cell. So the computer can then give a readout to the surgeon saying, yes, this is healthy tissue, or no, this is diseased tissue. these kinds of decisions for a surgeon are very powerful and helpful because in the case of removing a tumor, you want to save as much of the healthy tissue as you possibly can, but you want to cut and you want to make sure you cut out all of the tumor tissue. So by having this and by doing the kinds of metrology that we do in MPL, it gives much more confidence to people taking those measurements. So do go and have a look at the things in those labs. The slide is very slow. So this slide here is just really telling us about the things I did earlier in terms of seeing where the drug goes. I just wanted to show this slide because I'm a physicist, and my movement into biology was really encouraged by this very famous clinical pharmacologist, Sir Colin Dollery. He founded the field of clinical pharmacology. He was at GlaxoSmithKline. So his work, and by focusing on that, has been able to make drugs much more effective for humans and been able to deliver them to patients much quicker. This is this instrument. It's so-called Orbisims. So this was the first one that I invented and was delivered to MPL in 2016. There are now over 20 of them around the world, and all of those are providing amazing answers to really tough biological questions that you can't get elsewhere. How are we doing for time, by the way? Yeah, perfect. Let's see what. So this is the kinds of things that we're able to do. So if you see the cell there, we're able to actually track how much of the drug molecule is in those individual cells. We can measure this with really high accuracy. But the other thing that's really amazing about cells, so if I had genetically identical cells all grown together and all incubated in a bath with this drug molecule in, you would expect that they would all take up the same amount of that drug. But this is exactly where biology is so much more complicated than physics, going back to my earlier statement. And oftentimes in biology now, we're really trying to do things at the single cell level, because if we measure the whole population, it kind of masks out the detailed information that we need to understand. So now by actually measuring this at a single cell by single cell level, we can see exactly how much drug goes in the cell, and we can see the metabolic changes that occur. We don't need to really see the detail of this graph particularly, but what you can see is that some cells take up a huge amount of drug. This is the amount of drug. And some cells take up hardly any drug, but they're all following on the same kind of line. So this is really telling you the biology is really complicated, but through the physics and the methods that we're using, we can see that the principles are basically very similar. So this was really actually kind of revolutionary data at the time in 2017. And this is now providing really important information for people in biology trying to look at things at the single cell level. So I think that pretty much takes me to time, and thank you very much.
Amazing, thank you so much. We have a couple of minutes for some questions. If anybody has a question, yeah, we have one here.
Hi, I read that there's a lot of research being done on taking medicines through the nose rather than through the mouth.
Yes.
And I just wondered if you work on this or you know about this.
Absolutely, yeah, no, that's a very good point. So, as I was saying, the drug molecules that are very good at getting in the body and be soluble are hydrophilic, and they're not very good at getting into the cell. Wherever the cell is, they kind of come to this waxy surface on the cell layer, and they don't get in well at all. But if you're taking the drug either in the lung, like an asthma drug, or in the nose, then you don't need to make it soluble anymore. So the people designing the drug can make it very happy to get into that kind of waxy, oily layer that's on the cell membrane, so they can be much more effective at getting into the bloodstream. So yeah, it's a very good route for taking drugs.
So would it affect that graph?
Yes, yeah. So I mean, in this case here, these actually are rat alveoli macrophage cells, and so these are the cells that would be in the lung. And by delivering it directly to the lung, then you would be able to increase the efficiency of getting the drug, so you could use a lower dose. So it's a really good question, and I think a lot of work does go into this, trying to optimize, a bit like the speaker was saying before, reducing the amount of overall dose to the body and trying to improve the dose to where it's going. But yeah, the UK actually is massively strong in respiratory medicine. So it's a great UK strength.
We have another one, just with the map in your hand there.
I had a question about those lipid membranes, and is the nucleus of the cell, that's also a lipid membrane?
Yeah.
Right? So those vacuoles, those where they have the mRNA for the vaccine and everything, does that stop at the outer membrane, or does it go all the way through to the inner membrane?
Yeah, that's a very good question. There's a really complex process of these lipid vesicles going in. It's called endocytosis. So kind of when they kind of like dock onto the membrane, and then it absorbs it and then comes through. But then there are other parts in the cell that then start to sort of break that down, and it's a kind of complex process. I mean, I'm not a biologist, but biologists would tell you, I think there's like multiple stages of this so-called endocytosis. And it's kind of tricky, because, and it's a big area of research right now, because RNA is quite fragile, which is why you go to a lot of trouble to protect it. And they want to try and get enough of this RNA dose into the cell to get to the mechanisms, basically, where you have these the ribosomes that will then convert it to the protein. So yeah, it's a really complex process, and we do actually collaborate with some of the pharmaceutical companies on exactly that question.
It's also the origin of why we have mitochondria in the first place, because in evolution that was the very first endocytosis that led to us eventually. I think that's all we have time for just now, just before our next talk. So if you're not sticking around for our next talk, please would you exit through the door that's over here, and Billy will help you. Thank you very much. Hello, thank you everybody for joining us for our final talk of How Long is a Piece of String, which is our talks program for Open Day. We hope you have had a great day looking around our 55 plus exhibits. There's lots more to see around the place if you haven't, and also the talks are finishing just after Emma's talk now, but we will be showing them again. So if there's any of them that you really hoped you could have seen and you've missed, we'll be showing them again in here afterwards. Yeah, without further ado, just a couple of pieces of housekeeping. Fire exits are the two doors behind you where you came in, and this door down here, just in case there's an emergency. When you're leaving the theatre, if you wouldn't mind just leaving through the door over here on your left, my right, and if you wouldn't mind just checking your phones are on silent as well, that's really, really helpful. So next up we have Emma Williams, who is going to give her talk on measuring a rising tide, talking about satellite observations of sea level. So having accurate measurements of rising sea levels is really critical to predict the future of coastal regions, and there's a few ways to do this on land and at sea, but sometimes it helps to have a new perspective on a situation, and that's where satellites come in. So Emma is a principal scientist in climate and Earth observation at MPL, and is going to talk us through how the Copernicus Sentinel-6 mission tracks shifts in ocean height and a 30-year record of global sea levels. Thank you so much to everybody for being part of us today, part of our 125th anniversary today. We really hope you've enjoyed the day, and please continue to take a look around all of our amazing exhibits, and welcome Emma.
Thank you. Thank you very much, everyone, for coming to this talk, and I hope you're having a great day here. I'm here to talk about climate change and about rising sea levels. And I was told that the theme of the set of talks was on myths and how we can correct myths. Now, there are many, many myths about climate change. And actually, I'm going to try and, if I remember to start my timer, I'm going to stop with enough time to answer any questions you have about my talk, but also about climate myths. One of the most, I think, important climate myths is that it's either we know everything or we know nothing, and neither of those positions are true. Just because we don't know everything doesn't mean we know nothing, and because we know a lot doesn't mean there isn't still research to do. What we're doing at NPL is supporting a whole community of scientists all over the world who are trying to understand how the Earth is changing using satellite observations. And maybe some of you have already seen, but if you haven't, some of my colleagues are also talking in the next module along downstairs around a big glowing globe and in a laboratory in module F4. So I'm talking about sea level, but before we do that, I want to start with this picture. I like to start my talks with this picture. This picture is a photograph taken by a human being with a camera with a film in it. So when the Apollo astronauts were on their way to the moon, they were given film cameras to take photographs of the moon. And then they looked out the window and they saw this. And they realized that the real thing to photograph was not the unknown moon, it was the known Earth, and seeing that known Earth in a completely different way. And we've seen so many of these photos now, we can all access this on our phones. We've forgotten, to some extent, the power that this image had. In this image, you see the whole Earth against the vast blackness of space. This is our planet. This is all we've got. The atmosphere is a tiny, tiny thin layer around this planet. There are no political borders. Indeed, there are these enormous weather systems that cross continents. We're all connected. We're all on this planet together. And when we really, truly understand what that means, we want to protect it. And this image, this photograph, led to the beginning of the environmental movement. It gave people the awe, the care. Now, the satellites that I'm going to talk about, they make much more sophisticated measurements than a photograph. They make, even when they're taking photographs, they're now taking photographs in lots of different parts of the electromagnetic spectrum, lots of different colours of bands. But there is still this underpinning awe to all the measurements that are being taken. And however sophisticated those measurements are, we're aiming for the same thing, to help people understand the Earth and want to protect it. The climate change is a real complex systems problem. The Earth system itself is extremely complicated. If you change one aspect of it, it affects all sorts of other aspects. The human system is even more complicated. Our politics, our societies, the way we've carved up this planet into individual groups. But fundamentally, if you're going to try and resolve an enormous existential problem in a complicated world that is complicated both in the physics and in the biology and in the human sociology, you need data. And you need data you can trust. You need to be able to say that you can monitor the unexpected changes that are a consequence of our actions. Because even when we're trying to do the right thing, a system this complicated, we can get it wrong. Or maybe it's not quite as bad. And the more measurements we take, the more we understand this Earth, the better. I want to talk, there are many, many satellites up there, and they measure all sorts of things. And my colleagues in the other Climate and Earth Observation groups in the map will talk to you about the optical satellites, the satellites that measure the amount of light reflected from the Earth or the amount of infrared energy emitted by the Earth, and what that can tell us about how much algae there is in the sea, how healthy the rainforests are. It can talk to us about all sorts of things. But I want to talk to you about Sentinel-6. Sentinel-6 is a radar altimetry project. Because my husband works in the 3D printing department here, I have a little model of Sentinel-6. Sentinel-6 is about the shape and size of a garden shed. And it is a radar satellite. That means it's pinging a radar down to the Earth and then measuring the reflected radar signal coming back. And by timing the time it takes to go from the radar to the Earth and back again, you can understand how high the surface is. And when the surface is the ocean, which is the predominant thing that Sentinel-6 is designed to measure, you can measure a rising sea level. Now, Sentinel-6 is a European Space Agency, NASA, EUMETSAT, NOAA joint mission. It is a continuation of a record that goes back to 1992. So the first radar satellites to measure sea level were launched in 1992. So just to put it into perspective, this is another thing my husband printed for me. This is a graph of sea level rise since 1992. So actually it's from 1992 to 2020. And this is the real amount that the oceans have risen in that time. Now, that is both a very big number and a very small number. If you think about how big the ocean is, how much of the Earth is covered in the ocean, for the entire ocean to go up this much is a very big number. At the same time, if you've been scared by sea level rise, you might think this is a small. Good afternoon.
NPL. Our talks programme has now ended.
No, it hasn't.
Head to the auditorium and catch up on any talks you have missed, as we are now streaming the recordings. Ask any of our staff to guide you to the auditorium. Thank you.
I'll just keep going. Was that the time I was supposed to have? So sea level rise, about 10 centimetres. It's accelerating. It's just over 3 millimetres a year, and the amount is accelerating. Now, the reason this matters is partly what's causing it. About half this sea level rise is due to melting ice. That's enormous ice sheets in Greenland and West Antarctica melting. That's the glaciers in the mountains of the world melting. And that melt is increasing the mass of water in the oceans. Now, we can test how much that rise is happening using gravity satellites. So there's gravity satellites that are measuring basically the gravitational pull of the Earth, and they can tell you how much mass is going into the ocean. Then in addition to that, the other half of that rise is thermal expansion of the oceans. What does that mean? It means that the sun is putting energy onto the Earth, and the Earth is then radiating that energy out into space. But there is a slight imbalance. Slightly more is coming in than going out, and that's predominantly due to the greenhouse effect. The greenhouse effect, by the way, is a good thing, because if there wasn't a greenhouse effect, we'd be at minus 15 degrees, and I wouldn't like that. Unfortunately, however, we're accelerating the greenhouse effect because we're putting additional gases that act as greenhouse gases into the atmosphere, and that's raising the height of the atmosphere that's radiating out to space. So if you raise the height of the atmosphere that's radiating out to space, you're radiating less out to space because it's cooler up there. And so you're having more heat kept inside the Earth system. Of that heat, you've probably heard about the 1.5 degree temperature rise of the air. The air only uptakes 1% of that extra heat. The oceans take in 90% of the extra heat. So almost all of the extra heat that's going into the oceans, or the extra heat that the Earth is holding is going into the oceans, and it's causing that sea level rise. It's also putting more energy into the oceans, which is increasing the size of storms, and it's accelerating the wind and therefore the size of the waves. And what we're trying to do is to understand that balance. Can we explain the heat uptake into the oceans by looking at the gravity satellites that measure the mass of the oceans and the sea level satellite Sentinel-6, which is measuring the rise in the oceans? And if we could take that measurement and measure that to 0.1 millimeter per year, then we would measure it well enough to be able to tell the climate scientists something new about the heat uptake into the oceans, and to see whether we're balancing our understanding, whether we have a complete understanding. And remember my point, just because we don't know everything doesn't mean we know nothing, but equally there is still stuff to learn. And one of the things still to learn is to test how that is being balanced. So we want to measure the rise in sea level to better than 0.1 millimeter a year from 785 kilometers up. It gets more complicated than that, of course, because you're 785 kilometers up, but between you and the ocean surface, there's an atmosphere. And the atmosphere, for those of you who understand physics terms, has a refractive index. For everybody else, it slows down the radar. And the more ions you have in the ionosphere, the more free electrons there are right at the top of the atmosphere. And the more water molecules you have in the troposphere, which is the bulk of the atmosphere, the more you're being slowed down as that radar goes down through the atmosphere. So we have to measure and assess the number of ions in the upper atmosphere and the amount of water molecules in the main bulk of the atmosphere, and we have to do that very well, which is why Sentinel-6 doesn't just have its radar, it also has a microwave radiometer, which is basically measuring the amount of water vapor in the atmosphere. It's also got all these instruments. These are there to measure the orbit, because if you want to measure 0.1 millimeter a year, you better know where your satellite is to better than 0.1 millimeter. Now that's not as easy as it sounds. You're up there, you have various gyroscopes on board, but you also have some instruments here that can connect to the GPS satellites. You've got some instruments on the ground that fire up lasers to this to try and take a measurement in the other direction. You've also, there's all sorts of instruments here to try and assess the actual orbit of the satellite. But you also have to take into account this orbit, this satellite, in order to keep itself at 785 kilometers above Earth, is using a bit of fuel just to keep itself aligned in the right way while it goes around the Earth. And so the fuel tank is emptying. And if the fuel tank is emptying, it's changing the center of mass of the satellite. And you have to take into account how the change of mass in the satellite changes the distance between the center of mass of the satellite, which is the point that's doing the orbiting, and the microwave antenna. So there's all sorts of things you have to worry about even before you get your signal down to the ocean. And then you hit the ocean. And you can see the problem with 0.1 millimeters a year. And so what is called significant wave height really matters. Now, the satellite is not measuring a single point on the ocean. The satellite is measuring over about 300 kilometers of ocean. And it's looking at some sort of average signal from this field. So we have to think about how do we handle waves? I'm just going to leave this running for a moment because I like this. So we have the ocean. If you have a look at the waves too, you can see them a little bit here. They're peaky at the top and they're sort of flatter at the bottom. Maybe you can see that. That affects the maths because what's the midpoint in the wave? It's actually lower than you think it's going to be because of the peakiness of the waves. There's also an issue that the signal that comes back is coming back better from the bottom of the waves than the top, simply because at the bottom of the waves, when the radar comes down, it's going to go straight back up, but from the side of the wave, it's going to go off in the wrong direction and could be missed. So you have to take all this into account, and then fundamentally, the way the measurement happens is this. The thing pings down its radar, and at some point, the radar starts to hit the very top of the waves, and the signal begins to go up. Then, of course, as the radar comes down, it starts to measure more of the waves, and then it comes to a peak, and then it starts to come down. And by looking at the shape of this waveform, this radar time response pulse, we can tell all sorts of things about the surface. How slopey this is on this end, that will tell us about how big the waves are, because the bigger the waves, the more slopey it is. How high it goes will tell you how rough the waves are, and that's when I'm talking about those tiny little ripples on top of the big waves. And there's all sorts of other things you can tell from the shape of this. So scientists who work with this, they're trying to understand and solve all of these issues. And I've come into this project relatively late. So we at NPL have been working with optical satellites for a very long time. And our job as NPL is to provide traceability. That means what we're doing is we're looking at comparing the satellites with one another. We're looking at assessing uncertainties in the satellite measurement. Because what we want to say is if climate change takes a long time, yeah? If you think about even the temperature one you're familiar with, 1.5 degrees, it changes a lot more than that between night and day, between summer and winter, between North Pole and equator. So to see that 1.5 degrees, you need to take measurements all over the Earth, and they need to be equivalent. You couldn't have a bias between the measurements in one country and the measurements in another place. And because you're going to want to see a very, very small trend, you've got to take measurements for several decades. And to take measurements for several decades, you've got to know that that your measurements today are comparable with measurements from 10 years ago or 10 years into the future. So what we need to do is we need to ensure the stability and equivalence of this, and that's something that NPL has been doing for 125 years. Yeah, the meter today is the same length as it was 125 years ago, and it is the same length as it is in every other country in the world. And that's because in metrology, our job is to keep the stability of measurements. So that's what we're trying to assess. And so we're trying to bring those things, and we've been bringing those concepts to optical satellites for a long time, and now we're going to start, we've recently in the last 4 or 5 years been starting to bring them to the altimetry satellites. And that has meant understanding all these processes I've talked through about, and to look at ways of doing comparisons between different satellites, to do measurements on the ground that can be used to compare to the satellites, and to work through and try and understand how we can do better at understanding the uncertainties in this measurement so that we can get them from where they are at the moment, which is about 0.5, 0.6 millimetres per year when they've averaged everything, to getting it below 0.1 millimetre a year so we can do more information. And I was at the European Space Agency on Monday this week, where I'm involved in helping them. I'm in a mission advisory group for Sentinel-6 Next Generation, which is designing the satellite that is going to be launched in 2035 to follow on the Sentinel-6 time series. And in that group, we're making decisions about whether we should have a better radiometer on board with more frequencies in the radar, or with a better radar on board, or a better radiometer on board to get better accuracy measurements of the atmospheric delays, or whether we just need better models of the ocean waves and how the radar interacts with them. So one of the things we're doing here is to take part in mission advisory groups with the European Space Agency to help them with those decisions and to come into those discussions with this metrological focus about uncertainties and comparison. Thank you.
No, I'm not. Thanks so much, Emma. Have we any questions for Emma from the audience? Straight away, one. Yes.
Are there any comparative studies with other countries doing these radar measurements that you can compare to make a conclusive decision on?
Yes, thank you. That was a good question about whether there are comparative studies with other countries with the radar satellites. So in the optical satellites, every country builds their own, and there is lots of work going on to do comparisons between them. So our colleagues in Module 4 will tell you about their site in Namibia, where they measure the reflectance of the ground and the clarity of the atmosphere. And the European satellite flies over on Tuesday morning, and the American satellite flies over on Wednesday afternoon, and you can compare them because you've done the measurements on the ground. So in the optical area, we work on a lot of satellites like that. In the radar area, these satellites are very expensive and very complicated. And actually, you'll see that Sentinel-6 was a joint mission between the European Space Agency and NASA. And that's generally the case. However, so there is not another country building their own version of this. However, what there is satellites that do a different job. So Sentinel-6 is designed to be a reference altimeter. That means it's on a track that does not alias with the tides. I didn't mention tides, but you can imagine they're also an issue you have to think about. A lot of satellites follow a sun-synchronous orbit, which means every time they cross the equator, it's the same time of day. Now, the problem with a sun-synchronous orbit is that the sun creates some of the tides. Obviously, the main tide is from the moon, but there is also a solar tide. And so if you're synchronous with the sun, then you always measure when the sun is at the same location. And so you're always measuring one particular part of the solar tide. So Sentinel-6 is in an orbit where it measures, where it's intentionally mismatched with the sun. There are other satellites like Sentinel-3, which has both optical instruments and radar instruments on board. And Sentinel-3 is sun-synchronous because its optical measurements needed to be, and because it's doing slightly different. It's more focused on ice in the Arctic Ocean and around Antarctica, sea ice. And because it's more focused on those, it's in a sun-synchronous orbit. But one of the projects that we have at the moment is comparing Sentinel-6 with Sentinel-3, even though because they're both measuring height of the oceans, but they're in these totally different orbits, so they've got these different aliasing with the tides. So we do comparisons between those. We also compare Sentinel-6 with itself, because if it's done one orbit, when it comes round on the next orbit and it's going sort of back up and the Earth has turned round, it actually has a crossover where it sees the same location sort of within a couple of hours to a few days after the last time it went over that point. And of course, the atmosphere has changed, and the tides have changed, and the significant waves have changed. But the argument that is in a few days, the fundamental sea level has not changed. So you can test how well you've done your corrections using those crossovers. So long answer to your question, but we do think about the ways that we can compare satellites. Yeah.
Question. We are told that the Earth's atmosphere is warming up,
Yep.
and it's causing all these disasters of landslide and floods here and floods there and tornadoes. Does any of this contribute to looking at these disasters happening around the world?
Yes. So Sentinel-6 itself is focused entirely on sea level. It's a dedicated mission for sea level. But as I said, a lot of those disasters come from the energy in the oceans. So what we're doing is it's slightly more fundamental than direct. We're looking at the question of can we explain the heat uptake by the oceans? Because if we can explain the heat uptake by the oceans, then we are assessing our understanding of the system and our ability of our climate, our weather forecasting models to predict such storms. So, in order for the weather forecast, the weather forecasting models are basically big equations. They're running on the biggest computer in the UK is owned by the Met Office. You know, the biggest computers are running the weather forecasts, and they are basically solving a whole load of equations in little boxes all over the Earth. And they are, and in solving those equations, they are trying to understand what's going to happen. And behind those equations is physics. And missions like this are testing that fundamental physics, so understanding this better will eventually lead to better predictions in the weather models. But equally, there are loads of other satellites out there that are looking directly at disasters, and because Sentinel-6 and Sentinel-3 can, because that slope of that thing can tell you about wave height, they can sometimes be used for also assessing wave heights and therefore steering ships in the right direction. So not indirectly with this satellite, but there's lots of other satellites, and the type of techniques we're doing at MPL are affecting them all. Thank you.
So you need AI data as well as the old style data would be hand in hand for advanced technology in the future of research.
Yeah, that's another.
How would that work within this method?
Yeah, another brilliant question there. If anyone didn't catch it, that AI is becoming very, very important, and what impact does that have on all of this? So as I was saying to our colleague over there, the ocean, so the weather models and the climate models at the moment don't use AI. They're based on physical models and our physics understanding codified into equations. There is a move towards testing the ideas about whether AI can, first of all, do equally and then potentially do better at doing things like weather prediction, at doing things like understanding even specific models. And it's still quite early stage. So a lot of it is, and there's also what's called physics-informed machine learning. So where you can do the mixture of the sort of AI and machine learning, but you inform it with your understanding of the physics. So there's a lot of research in this area, and this is probably what's going to become big in the next 10 years. At NPL, we have a data science department who's already very working hard on AI and answering the same kinds of metrology questions, like how do you trust the output? AI tends to be a bit of a black box. So thinking about how you can validate and help ensure you understand the output of those models is some work that we are doing. In my own area, we have some preliminary projects with a few groups who are looking at AI. And I had a conversation with somebody from the Alan Turing Institute, who actually said that our work at NPL may become even more important, because at the moment, to get to the weather models, you've got these physics, you take a measurement, you take the radar signal, and then you do a lot of calculations to turn that into sea level. Or you take an optical signal and you do a lot of calculations to turn it into algae in the sea. But with AI, And the problem is that it's very hard for us as metrologists to assess the uncertainty through all of those calculations. You're getting further and further away from the measurement, and there is uncertainty in the models, which is very hard to think. With AI, you might actually get to the point where the AI can model not just the physics of the Earth, but also the physics of your instrument. And then, when you get to that point, and we're not there yet, but when we get to that point, having really, really robust data at level 1, at the earliest stage of the processing, which is the bit NPL can do the most value to, will be extremely valuable. So I think there's AI is the future. We're trying to prepare for it.
I think we often get people when we say we are the National Metrology Institute who think, is that about the weather? But this is a rare crossover between metrology and meteorology for once.
And there's even a joke that says the difference between metrology and meteorology is EO, which is the abbreviation for Earth observation.
I think we'll have to leave it there, I'm afraid. But Emma, you can go and visit Emma's lab and some other Earth observation stuff around. We have 55 different exhibits open, as I said, but please do pop by some of those scientists and ask them more of your questions. And then we will be replaying the talks in the auditorium. We're just going to have about a 10-minute break, and then they'll be playing in here. So yeah, thanks so much for your attention and for joining us for our 125th anniversary.